The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, are you guys all ready? All set? Okay. So my name is Vina Nguyen. I'm at MIT, going to be a senior next year. I'm studying electrical engineering and computer science. That's just one major, half of both. And I'm teaching probability because I thought it was an intro class that I really liked a lot. Hold on. Yeah, sorry. I speak kind of soft, so if you can't hear me, just tell me and I'll try to speak louder. Okay. So there's a few announcements I have to go over. First, you need to be here because you want to be here, not because your parents want to be here. So if you want to leave, leave, but I want you to take it because you want to take it. That's the best way to learn. During registration, you also got your sheet with the blank schedule. I gave you that sticker, so you can put it on there. Everyone did that? Okay. So next week, you should come to this room directly. So don't come to lobby 13, just come directly here. Okay, so on your registration sheet, they also told you about a server called Caroline. So for my class on the sticker, you need to type in the password, which is frog or something. And I'm going to post these slides up there or any lecture notes I had in case you missed a class or you wanted to review something. There is chat and forums, but I work full-time during the week, so I probably won't have time to always chat with you guys. But my email is listed on the syllabus if you do have questions. I always check my email, but I don't necessarily have time to chat. So email is good if you have questions. Fourth announcement, there's a lunchtime activities form you also got. You need to get that signed. Make sure you turn it in next week because HSSP won't take it the week after next week. And if you have any other questions about administrative stuff, go to the HSSP office because I'm just a teacher here to teach and I'm here to manage paperwork. Okay, so now that that's done, I'm going to start. Okay, so as you all know, this is probability. Told you a little bit about myself, but I also want to know a little bit about you guys. I have never been to Boston except for college, so I'm not entirely sure what it's like. If you could go around and tell me your name and what grade you are and what school, then start with you.
I'm Margaret Sue. I'm going to 9th grade and I'm going to Newton South High School.
Okay.
I'm Letitia and I'm going to junior year.
Okay.
In Wellesley.
My name is Iris, and I'm also going to Wellesley, and I'm going to be in 12th grade.
I'm Magnum. I'm going to be in 12th grade. I'm related to her. And yeah, so I go to Wellesley.
I'm Amy, and I'm going to 9th grade at Wesleyan High School.
Hi, I'm Anu, and I'm going to be a junior at Wesleyan High School.
I'm Priyanka, and I'm going to be in grade. And I go to West Blanchard High School.
I'm Mega, and I'm going to 8th grade also in Stony Brook.
My name's Kevin, and I'm going to 7th grade. And I'm going to Boston Latin Academy next year.
I'm Diana, and I'm going to a senior year also, and I'm going to start Brigham High School.
I'm Andrew. I'm going to 7th grade. I'm going to Trinity Middle School.
I'm Ben. I'm going into sophomore year at Kingsman Oxford.
I'm Beer, and I'm going to 11th grade at Acton.
I'm Tina. I'm going to be a junior at Brady High.
And I'm going to 7th grade and I go to Wesley Middle School.
I'm Alan. I'm going to 8th grade and I'm going to Boston Latin School.
I'm James. I'm going to 8th grade and I go to Wesley Middle School.
Okay, so I guess we have a pretty good range.
Okay.
Thank you. So I'm sure you guys know this is all for beginners. If you already know this stuff, you have no reason to be here. There's lecture, I'm probably going to use mostly PowerPoint. If I do some things, I'll use the chalkboard, and we'll work out problems either as a class or I'll hand out stuff. And there is no homework, so. And please feel free to ask questions. I don't want to move on unless you guys understand it. It's like math, you know, everything later builds up on what you knew before. So, okay, so why should we study probability? Well, first you want to model the uncertain. It's easy to be like, oh, I don't know anything about this, so I can't decide anything, I can't estimate anything. But with probability, you can at least get a sense of what's going on with the world. And it's not just that you want to know what's going on, but you also want to decide based on it. And then for the third point especially, there's also studies out there in the news, you know, they make up some random statistic. I mean, not always, but it could sound that way. But if you have probability background, you can at least take a more intellectual approach to it. You can't just take it as is. You need to question other factors, or maybe there's, you know, a certain way of sampling that they did wrong. So this would help you to understand more what the studies are confirming or suggesting. Some examples are like, what's the weather like tomorrow? You know, sun, rain, how much %? What are the chances of a drug working? Depending on the factors of the person, you know, their age, their gender, their medical background, you know, how successful this drug will be. The third kind, what kind of customer will buy my product? Maybe based on their buying behavior or their demographics, how likely will this product sell to them? How profitable will it be? Fourth one, should I buy a lottery ticket? Will 2 help? And then there's also bio applications like whether your child will be a boy or girl. Hopefully you guys aren't there yet. So now that you know why we should learn probability, you should know there's 2 actually different definitions for it. The first one is frequency probability, which is the more physical, like if you repeat something over and over again, how often will the result happen? So how likely is a certain event that you know is the same every time is going to happen? And then the second one is Bayesian probability, which we will get to later. And that's a measure more of how likely, how sure you are that something will happen, given the evidence. So it's okay. So in Bayesian probability, unlike frequency probability, you can't repeat something over and over again. So you could, an example of that would be like, how likely am I going to get an A given that I attended all the classes or I participated or that? You can't repeat that experiment over and over again. It's a measure of belief. So is that clear to everyone? Okay. So we're going to look at frequency probability a little bit more. I'm sure you guys know that there's a 50% chance that heads will come up or tails will come out when you flip a coin. But how exactly are you going to measure that? I mean, you could flip it once, or you could flip it twice, you could flip it 3 times, or you could flip it a lot of times and then figure out the ratio of heads to tails. So, so we're gonna do not necessarily like an experiment. I have a coin, and we're going to flip it a large number of times. And I want you to observe the % of heads that comes up after each time. So you want to take the average of heads that comes up after 1 time, after 2 times, after 10 times, etc. And what I want you to do is observe what happens initially, so after like 1 or 3 times, and then what happens after a while. So what I actually have here is an Excel sheet. If you can see that on the left column, it's a number of trials. The second one is a 1 or 0, 1 being heads and 0 being tails. And then after each time, it calculates the ratio of heads. So the way we graph this, can everyone see this? Yeah, okay. So, a probability goes from 0 to 100. So that would be, 0% heads and then 100%. And you're expecting around 50%, right? So that's 50, 10, 20, 30, 40, 60. Okay. And then your x-axis is the number of trials. So the number of times you flip your coin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we have around 15 people, but probably go up to like 20 times. Okay. So I have a coin, and I want each of you to flip it and tell me if it comes up heads or tails, and then I'll use the Excel chart to calculate it. Okay, go ahead. Heads. Okay, so right now your ratio is 100% because 1 out of 1 heads. You give it to the next person behind you.
Tails.
Tails? Okay, so 50%. Next person. Tails. Okay, so now you're at 33%. Just like around here.
Tails.
25%.
Heads.
40%.
Tails.
Tails. It's 33%. Tails. 29%.
Tails.
25%.
Heads.
It's 33%.
Tails.
30%.
Tails.
Tails. 27.
Heads.
Heads. %. Was that the last person? Okay. Oh, go around. Okay.
Tails.
Tails. 31%. Heads. 36%.
Heads.
Heads. 40%. Okay. So not done yet.
First. Heads.
44. Tails.
Anybody else?
Anyone else? No.
No.
Thank you. Okay, so we have a pretty small group. If you were to take just that experiment, you would assume that heads showed up about 40% of the time. That's not true, right? So you need to have a larger sample. So in this one, you guys can see that I auto-generated the same experiment, but 500 times, which we can't do today. It would take way too long. But if you can see, like, at the beginning, which is kind of what we did, you know, it varies a lot at the beginning. About 20 here would be like this part where it's still very variable, but after a very long number of times, it'll eventually converge to 50%. So this is actually the law of large numbers, but I mean the explanation for that we can cover later. But this is just an example of how you would figure out what a frequency probability is, and you need to know like how many times you need to do that. So this law is only relevant for large numbers, hence large number. So does that make sense to everyone? Okay. Before we do probability, one of the very important things is set theory. I can't remember if high school taught you guys that. Do you guys know what set theory is? Just a little bit basic understanding? Okay. Well, I'm just going to go through it just in case for you guys who need that refresher. So a set is a collection of objects. For example, there's outcomes of a die. You can have 1, 2, 3, all the way to 6. And each object in a set is called an element, and each element needs to be unique. So if you have a collection, say, of 1, 1, 2, 2, that's not a set. It has to reduce to 1 and 2. There's different kinds of sets. You can have your empty set, which is represented by the 0, the cross. There's a set with an infinite number of integers or elements. An example of this is set of integers. You know, it can go on -1, 0, 1, 2, etc., etc. So even though it's not a finite number of objects, it's still considered a set. You can have subsets. So if you have a set H, then subset H is a subset of G if every element in H is in G. So if H was a set of 1 and 2, then that's a subset of G as well. And if every element in G is a subset of H, then that means they're equal. And then you have your universal set, which is symbolized by the omega there, and that means it contains all the elements possible in your context, in your problem context. So this is a more graphical look at it. So like assuming that your universal set for this context is all integers or all numbers, then you have like 1000, 53.6, or any number. And then your set G would be all the integers, and then H, which has 1 and 2, would be your subset of G. So G encompasses H. And does that make sense to everyone? Okay. There are set operations you can perform. First one is complement of S, which, S is like just a random set called S. So complement of S means all the elements that are not in S. So the red here means that those are the shaded areas that are not in S but are in the universal set. Is that clear to everyone? Okay. And then the second one is union of sets, which means all elements in S or T or both. And that's symbolized by that U right there. So if you had a set that had like 1 and 2, and then T had 2 and 3, then your union of sets is 1, 2, and 3. So you don't count 2 twice because elements of a set have to be unique, right? Okay. And then your intersection of sets means all the elements in both S and T. So given that example I had before, then your intersection would only be 2. So does that make sense, everyone? Okay. So I just want to make sure you guys get it. Can anyone tell me what the first one is?
shaded. You want the shaded?
Yeah.
Okay, so complement of S.
And the second one? Yep.
Complement of T.
You sure? Oh, sorry, second one is this one, right? Yeah. So complement of T would mean this area and that area, right? But because T is shaded, it can't mean not T. So can anyone help her?
Is it complement of S plus union of S and T?
Yep. Can everyone see that? I'll just write the answers. Okay. So your first one was SC. Can everyone see this? Can everyone see this? Okay. So you said complement of S union T, right? Does everyone see why that's right? Your complement of S would be like.
Yeah, it's I mentioned intersection.
Oh, okay. Well, it's actually union. Sorry. Wait. Complement S union T. Yeah, it's
intersection, which is what I meant to say when I said union.
Wait, sorry?
It's intersection, but I said union by accident. So I think it's union.
It's union. Yeah. Because if you said union and T, then none of this could count, right?
Oh.
Yeah.
Oh.
Is that clear for everyone? I can. Okay, so you have your SC, right? Plus T. Yeah, it can't, yeah, okay, does that make sense? Actually, S was this part too, sorry. Okay, so the third one?
Intersection of ST. Wait.
Complement, right? Yep. Okay, did everyone hear that? He said it was intersection of S and T complement, so complement of the intersection of S and T. I'll do that again. So S union T complement. Does that make sense to everyone? Okay. And another way you could write that is complement of S and complement of T. Does everyone see that? Yeah? Okay. So 4? Yes. And 5?
Union set of T. Complement of T.
Complement of T.
With the union set of S and T. Okay.
Close.
Complement of T intersect S. Intersection with S.
Yes. Yeah. Wait. Yeah, okay. So that would be, right? Okay. Does everyone see that? Okay. And the sixth one?
Complement of the union of S and T.
Mm-hmm. And given this example, can anyone tell me a different way to write the sixth one?
Complement S and union of
This one? Intersection.
In the intersection.
Yeah. Okay, does everyone see that? Okay. Okay, so that's a very abstract thing, but it's very fundamental, or everything else doesn't make sense. Okay, so probability models, your sample space is kind of like a set, right? You need to know what are all the possible outcomes. So that would be your universal set. You know, it has to be exhaustive. You can't leave out any events or your probabilities will not be correct. And none of the events can overlap. So every result that can happen has to be uniquely defined within your context. And then the events are a subset of your sample space. They don't necessarily have to be like probability of die being 1. They could be probability of your result being even. So it doesn't necessarily have to be just one. It can be a couple of events that can happen. And you also need probabilities. So that's your quantitative measure of the problem. So if you were to model rolling just one die, what would your sample space be? Anyone?
It would be numbers 1 through 6.
Yep. And what kind of events would you have? Like, event that you roll a 1? Is there any other kind of event? Yep. Or it could be like event that you roll greater than 4 or something like that. And then you need probabilities for that. So even number would be like 1/2. Greater than 4 would be like 1/3. Or probability of 1 would be 1/6. So what if you needed to do 2 die? Then how would you represent what that problem space is? Anyone?
Depends on what event you're talking about. Like if you want to do sum, then it'd be 2 to 12. But if you want to do pairs, then it'd be 1 of those.
So that would be like events, but in terms of sample space, you only can have certain results that come out from your die, which would be the combination of numbers, right?
Oh, so we're talking only about combination because could you also do stuff like what's the chance that you get a pair of numbers that are the same?
Right, so that would be an event, but not part of your sample space, because your sample space is the actual physical results that can happen, like a 1 and a 1, a 1 and a 3, and then how you interpret that is an event. So I guess I've kind of given it, but where's my chalk? It would not be the same because you're rolling 2, right? Yeah. Yeah. Right. So I'll get to that later, but the more basic thing. Can you guys see this? I don't. Kind of. I just. Okay. So, like, you were right about representing it, but for what it actually is, your sample space would be like 1, 1. Right. That would be the roll of your first die, the roll of your second die. Yeah, just like really basic, yeah. Like that. So that's your sample space. Yeah. I'm not going to. I can assume that you guys can figure that out. But is that clear, like how that's separate from an actual event? Yeah. Okay, so that would be like your sample space. But like what you mentioned, what's your name? Yeah. Okay, what Magnum mentioned is that the events, like the sum, like the probability that your sum is 12, that's an event. But that's not part of your sample space. Is that clear, how that's different? Or like the probability that you get doubles. Okay. So, do you guys understand the difference between like your physical sample space and the different kind of events you can get from it?
Is the sample space basically the exact values that you actually get?
Like your exact outcome, the bare bone. And then your events would be how you interpret it. Is that good? Okay. And probability is just like what's the probability this will happen? What's the probability that will happen? I know this is 1/6. I will figure that out later. Okay. So going back to what you said, how you represent this is pretty much up to you. The standard way is what you mentioned. What were you saying again?
Table where you like have 1 through 6 on the top.
Right. So you're talking about like this, right? Is this what you're? Yeah. Okay. So this would be your first die. Yeah. And this would be your second. 1, 2. Okay, so that's one way to represent your outcomes, right? So like probability of doubles would be these diagonals. Does everyone see that? Okay, and then 12. Oh, there's just one. Okay, so that's easy. Is there another way to represent sample space? I just left that there so you guys can draw. Is there another way to represent how your experiment will progress?
Graph.
Graph? How would you graph it?
Like 1, 2, 3 on the like 1 through 6 on the x-axis and 1 through the y.
So it's kind of like this, right? Except like it's like a grid, you would just put it here, right? So yes, you're right, but it's kind of like this already. Is there another way? How much time we have? Okay, well, what if you did like a tree, right? So like you roll it once, you get a 1, you get a 2, you get a 3, 4, 5, 6, right? And then you would just expand this. 1, 2. Right. So that's just another way to keep in mind. For this example, it grows exponentially, so it's not the best way, but it is a good way for certain contexts. So does everyone see how that works? Okay. And we ended kind of short because I wasn't sure how long this would take. So I want to make sure you guys know why we study probability. You know, there's lots of reasons out there. There's 2 different definitions. I know that's not entirely intuitive. So it's either how often something happens given a number of repeatable experiments, or the second definition, how much you believe that something will happen given the evidence. And then basic set theory, you guys seem to pretty much know that. Wasn't sure how much knowledge you guys had. But if you do have any questions, don't hesitate to email me. I can go over that with you. And probability models are important. So you can take, you know, a certain puzzle or problem context in your mind and graph it out in something that you can actually work with. So does anyone have questions or anything about the class, probability, HSSB? Was this too fast or too slow? I'm not really sure the knowledge you guys have beforehand. No? Good pace? Okay. Next time I'll fill up the time. I'm sorry, wasn't sure how long registration was going to take.
Could we go over set out right?
Yep. Okay, so do you have like a certain question or just want to go over it?
No, just in general.
Just in general? Okay. So, do you know what universal set is? Right? Like all the possible things that can happen is a universal set. And then if you have a set, so say your set is all the combinations that are doubles. So that would be, S would be like 1, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So this would be set S. And then complement of S is anything that's not an S. So that would mean anything here that's not a double. Does that make sense? So complement of S is anything that's not an S, but within your universal problem context. Good? Okay. So union of sets means if you have two different kinds of sets, it's everything in S and T. So if you had T could be that you rolled a 6 in either one of these. So like this would be T. I'm sorry, it's so messy. And this would be T. Can you see that? I'm sorry, it's a little messy. Okay. So your union would be this block, this block, this block, this block, this block, this block. Everything here and everything here. So that would be your union. And like I said before, even though you might have an element in both sets, when you do write out your set, you only count it once, because every element has to be unique. Okay?
Does T stand for something or just like
T is just a random name. You can be like set A, set B, set X, Y, Z. I just did it because it's the next letter after S. Is that good? Okay. So your intersection of sets is anything that's in both. And given this example, the only thing that's in both would be 6, 6, right? So your intersection would be just 6, 6 equals S intersect with T. Okay? Is that clear? Did you guys have any other questions about these things?
Oh, no, about that.
Okay, go ahead.
I was wondering, like, could you give us an example for the Bayesian probability, like in a situation?
Okay. So there was a pretty simple example I gave you about the like how confident am I that I'm going to get an A or something, right? But another basic example is like, say you noticed that your neighbor's grass was wet when you came home. And that's an event, but you're not sure whether it was because of their sprinkler or because it was thunderstorming this morning or because, I don't know, there was a flood. So you have to take the probability of each of those previous events. So like, what's the probability that he has a sprinkler? If it's 0, then you can kind of say that's less likely unless he got one today or something. Or if you live in California, you know, the probability of a thunderstorm is lower, so you also can kind of get a sense for how likely it was a thunderstorm or not, right? I don't know about floods in California, but it's kind of like that. Like you have previous probabilities that you know about that are related to your current problem, but you can't exactly know, but you can kind of quantify it given the previous evidence. Does that make sense?
Yes.
Okay. Anybody else? Or any other non-set questions or set questions? No? Okay. Well, I guess you guys can just finish off the cookies. And if you do have questions, then you can come to me like right now after class, or you can email me. My name is Vina again, and I hope you guys have a good rest of the day. Oh yeah, you guys should go back to lobby 13 at 3 so you can choose your last class. Okay? Yep.